Okay, in this podcast, we're going to learn about the ideal gas law. In all of the podcasts so far, we have been dealing with gases and the changes that the gases can go under.
So how's this one different?
Well, the ideal gas law really just deals with the property of a gas.
Okay, so I see there we've got pressure, temperature, volume, and moles.
Yeah, so we're adding in moles here,
Oh,
which means we actually have to go back and do some stoichiometry
That
sometimes.
that sounds like stoichiometry.
Yeah.
Remember, moles talks about how much of a gas you have, so that's an important property. How much gas are you talking about? Moles.
Yeah, so basically with the ideal gas law, if you know any of those three properties that are listed there, you can figure out the fourth.
That's useful.
Yeah, so we can know about the gas. All right, so what exactly makes a gas ideal?
It not being a liquid or a solid?
Not quite.
Ideally, that would be the case.
Ideally, I suppose.
Ideally, okay. Well,
But actually,
it has to do with just really kinetic molecular theory, because you have ideal gases, which kind of only exist in the imaginary world,
yeah, and we like the imaginary world though. So
because
that's
it
good.
makes math easier, and
Yeah.
easy math is great. And then what gases really behave like. The ideal gas law works well most of the time, but it has some assumptions. The first one, it's kind of like kinetic molecular theory. We've already talked about these. We assume that gases don't have volume.
But we do know for a fact that gases actually do have volume.
Yeah, they're matter. They take up space.
Yeah.
But for the math, they don't have volume, because then you have to figure out the volume.
Yeah.
And we assume that they are completely not attracted to each other at all.
But again, with the real gas, the molecules actually are attracted to each other. But we have to keep in mind that in a gas, the molecules generally are pretty far apart. So the interactions are actually going to be so slight that we just assume that they don't have any of those attractions.
Yeah. So it works out well if you just assume those two things, because the math is easier. There are two cases you need to know, though, where the ideal gas law does not work well. And that's because that's under high pressure and low temperature.
Yeah, under high pressure, the molecules are going to get close together because they're going to be forced together by some outside sort of pressure. And then the low temperature, the molecules slow down, and when the molecules slow down,
They're actually attracted to each other a little bit more.
Yeah.
So that's when those real gas law properties they're more significant under high pressure and low temperature. They get really attracted to each other if they're close together, or if they're moving too slow, when they pass by, they'll be close to each other.
Let's take a look at it. That one looks like the combined gas law we have. We're used to pressure, temperature, and volume, right?
yeah. So if, with the combined gas law, if the pressure or the volume or the temperature changed, we could solve for the new pressure, volume, or temperature, depending on what we know and what we don't know.
There you go. So, but we don't want it to change, so we're going to kind of rearrange this a little bit. We're going to move the temperature to the other side with a little bit of algebra. PV equals T. And we're also going to introduce moles. Now, moles is represented by the variable N, so keep that in mind in the equation for N. But the units on all of these, they don't really seem to match. You've got pressure,
In what usually ATM, right?
atmospheres,
yeah.
volumes in liters.
Yeah.
Moles are, well, they're moles.
Moles are moles.
And
Yeah.
temperature is
Kelvin.
Kelvin, right?
Yeah,
Not
Kelvin.
degrees Celsius, Kelvin. So none of those units match. So how do we get this units to match up? The answer is R.
R, the gas constant. All right.
All right.
All right.
All right. All right. R is the gas constant. That is a new term you're going to need. That number, the gas constant, it's a constant. It's never going to be given to you explicitly in a problem. Gas constant, where in the world does that gas constant come from? Well, let's rearrange it here and you can get a little better of idea. If we take that equation and we put R all by itself,
So we're solving for R here, right?
yeah, just solve for R. You get an equation for the gas constant, PV over NT. Now, this is only done under standard conditions. You will never have to do this again. This is a one-time thing to figure out what R is. Standard conditions. So let's put in all these numbers for standard conditions. Pressure. Standard pressure is
1 atmosphere.
1 atmosphere, or
Any of those other numbers on the back of your periodic table?
Any of them. We're going to use atmospheres, though, for this sake. What is standard volume?
That's a good question. 1 liter.
No.
Oh.
No, it's actually 22.4 liters. That's your next podcast, so just work with us for a second. Standard number of moles, 1.
Nice and easy.
Nice round number.
Like
Standard
that.
temperature, 0 degrees Celsius?
273 Kelvin.
Oh, 273 Kelvin. They're the same
Nailed it.
number?
Yes.
Yes, but it needs to be in Kelvin because you don't want to put a 0 in the equation.
Yes.
It needs to be in Kelvin. And then you have an equation and you get this number for R. 0.0821. There's the magic number. Memorize it.
Oh.
Or
do I have
don't.
to memorize it?
No, or you don't have to memorize it. It's actually on the back of your periodic table.
Excellent.
You will never be given this number in a problem. It'll never say, oh, this is what R is. But you always have it. You can always use it in the equation. It's on the back of your periodic table. 0.0821 R.
So I heard some people talking, though, that there's actually more than one R.
There is more than one R on the back of your periodic table. So the only difference is, look, you can change the pressure. 760 millimeters of mercury is the same as 1 atmosphere. So if you put that into the equation, you can get another value for R.
That makes sense.
They're both standard. You can use either one, but notice your pressure, whichever one you use, that's what your pressure has to be in. Your units have to match whatever these units of R are in. So all your pressures, depending on which one you need to use, is atmospheres or millimeters. Volumes need to be in liters, moles or moles, and temperatures in Kelvin.
All right, so some example problems with the ideal gas law. First problem, find the pressure in atmospheres of 0.024 moles of a gas with 1.5 liters at a temperature of 25 degrees Celsius.
All right, so there's a lot of numbers in here. I don't really know what to do. I'm just going to make a list of all the numbers.
I like that idea.
24 moles. Remember, N stands for moles. The pressure is unknown. 1.35 liters. What's that? Liters is...
Oh, volume.
That's a volume.
You might be thinking to yourself, why is N moles? Well, it stands for number of moles. And that, besides, M is mass anyway, so...
Is that what it stands
confusing.
for? N is number of moles? I actually didn't know that.
I actually just made that up.
Oh, okay. But
It sounds good, though.
If it helps you remember it, go with it. Temperature. I gotta add 273. Nothing in Celsius will work. Whoa, not 900. Just kidding. 298. So these are all the variables that are in a problem. P, N, V, and T.
I see something missing.
That's not enough to do the problem. The equation is PV equals N RT. What happened to R?
Oh, wait. We're just supposed to know that one, aren't we?
Yes, you are. It's on the back of the periodic table. There's 2 of them you can choose, but the question is asking for atmospheres. So we're going to choose the R value that has atmospheres in it. 0.0821 liters, atmospheres, there's that atmospheres, per mole Kelvin. Those are the units. Kind of confusing, but it brings them all together.
Yeah.
So this is just, that actually looks pretty good. It's just put it right into the gas law. PV equals nRT. We don't know the pressure. Volume there is 1.35 liters.
Does volume always have to be in liters?
It does, because the R, it has liters in the units.
Right.
N is 0.024 moles. R is 0.0821.
Uh-oh, it's getting close.
And temperature, we squeeze it in, 298
Just hit.
Kelvin. This is pretty easy then. Just plug it in and solve for the pressure, and you get...
Wait, we have to use algebra here, don't we?
A little bit. We just
my old friend, algebra.
You divide the nRT, divide it by the volume, move that over to get the pressure by itself, and you get 0.43 atmospheres. That was painless,
Relatively.
ideally. 0.43 atmospheres. Let's try another sample problem. They get a little harder, so I want to show you one more example. What is the mass of a sample of chlorine gas with a volume of 14.6 liters, 0 degrees Celsius, and 760 millimeters of mercury?
Let's write down our variables.
Variables.
First.
Mass.
Talk.
Mass is unknown, so let's put that there. Whoa, mass? What?
Mass, M.
We haven't talked.
We don't have an M in that equation that I know.
We don't have it talked about mass yet. That mass, I should just give up now because I don't know what mass stands for.
Yeah, it's probably, if you don't know what you're doing, you probably should just quit. That's probably the best option.
No.
Oh, wait.
Why are you telling me that? You're such a bad teacher. Temperature, 273 plus 0. Get out your calculators. It's 273 Kelvin.
That was a tough one.
And the pressure is 750 millimeters of mercury. All right. Now, there's not enough here to do the other gas laws, so we have pressure, temperature, volume. Remember, you always know R, 0.0821, right?
Sometimes, but I don't think that's going to work for this one because our pressure is in millimeters of mercury.
Oh, my pressure. Okay, let's do the other one then. The other one on the back of the table is 62.4.
Yeah,
liters,
that one has millimeters of mercury.
Millimeters of mercury, so they match. It's important for them to match R. Per mole Kelvin. Remember, that's on the back of your table. You don't need to memorize it. But the equation, again, is PV equals nRT. Mass is not in that equation. Help me out here.
It looks like we know 4 of those things in that equation, and N is moles.
Oh, so we can solve for moles. Well, then that makes sense because I can do moles and grams are related. Masses and grams. Stoichiometry.
Oh, that's right.
Oh, we're going to have to end with stoichiometry.
Who knew we'd have to use that
All right,
again?
let's do it. Pressure, 750 millimeters of mercury. The volume, 14.6 liters. I don't know moles, but I have the rest of it. 62.4 is R, and the temperature is 273 Kelvin. All right. A little bit of algebra here. And N equals what?
0.643 moles of chlorine.
Moles of chlorine.
Chlorine
Why
gas.
do I need chlorine in there? It's just moles, right?
Yeah, well, we need to find the mass, though, and we need to use the molar mass of chlorine.
Oh, because I got to convert moles to grams.
Yeah.
This is a molar mass problem. This is where you need your periodic table. Moles of chlorine, Cl.
Wait, I think something's wrong there.
Chlorine's Cl. That's chlorine.
Yeah, but isn't chlorine one of those diatomic ones that always comes in
Oh,
pairs?
there's 2 of them. There's 2 chlorines.
I'm glad we caught that.
That makes a difference.
Yeah.
Because now my mass, instead of being 35, is going to be 70. Because I need 2 chlorine, 70.9 grams of chlorine for every mole. Diatomic.
That was a good catch.
Moles are gone, and if you solve that out, we have grams, and your answer is
45.6 grams of chlorine.
of diatomic
Cl2.
chlorine. All right, so pay attention to that. Grams, your units need to match R. So if you've got masses and moles are related, so you can go between the two. It's tricky.